Okay. Hey everyone. We're going to get started in a few minutes, probably in the next 2 minutes. Before that, a few introductions. So this is Rohan. I'm from Sesh. So today, again, this is a wonderful opportunity for Sesh for organizing Hasgeek event, for providing space for a Hasgeek event, especially RootConf. So thank you again for Hasgeek and RootConf for giving us this opportunity for doing this. And it's not me alone. Again, it's not me alone. A lot of colleagues actually put in a lot of work helping me out, especially Danny, Davidson, Preeti, Nithas, etc. A lot more others, few more others. So yeah, I'll just talk a bit about the logistics. We have a few snacks and drinks, hot drinks in the pantry. The pantry is all the way over there to my right. The washrooms are to my right again, behind to my right. So that's mostly about the logistics. Again, I think that's mostly about it. I'll hand it over to Anirudh. So, all right. Hello, folks. Let me start by saying I am so happy to see so many systems geeks in one place. This is, I think this is like one of the best possible outcomes of the whole exercise of Bengaluru systems that we've been doing. To have an opportunity to take part in RootConf in organizing the distributed data systems track, and now this meetup, I think this is fantastic. So thank you folks for showing up. Before I get to Sesh's introduction, I also want to really thank the folks at Sahaj. Thank you so much for providing this space. I think this is a fantastic space. I'm sure we're going to have a lot of interesting questions, and we're going to have a generally awesome session. So today's session is something I've personally been very excited about. I think when most people talk about distributed databases, at least to me, there's an inherent element of fascination, because how did we take systems that constantly fail and make them coordinate on what are arguably some of the hardest things to achieve, right? Correctness in that sense. So everyone, please meet Sesh. Sesh is our speaker for the day. We have a round of applause for Sesh, please. So I think Sesh is the proper description of someone. So Sesh is the right person who you can describe as one of the most experienced veterans in the database space. Sesh has many years of experience, and similarly many patents and publications on a lot of things that define core to our database technologies of today. Sesh has worked at, has led teams and built awesome things at Google, at Yahoo, at a bunch of other very well-known companies. So yeah, that's a little bit about your speaker. And yeah, I think I'll let Sesh go ahead from here about the talk. I don't want to spoil the surprise. So yeah, here you go, Sesh. Off to you.
Hey, thanks everyone, and thanks for the folks. Likewise, before I start, let me really thank Sahaj for making this space available. I think it's a wonderful space. It's one of the best meetup spaces I've been to, and nice and open. And so thank you a lot. Then thanks to all the folks who helped me sort of prepare for this. Zainab made me meet a lot of people, and grilled me before I sort of passed the test. And here. So thanks a lot. I got awesome. And most importantly, I'm actually stunned at the attendance. I was considering erasing the C and the D and making this AI, but I made it as boring as possible. Like I said, I want to make sure people are really interested in this topic. They got it thought up, right? So I'm amazed at this speaks volumes of the system sort of strength that seems to be there in the community. So that's awesome. And like Anirudh said, I think this is going to be a topic where actually I'm not going to be delving too much into architecture and implementation. It's a little bit more about correctness and what is correct and what's not right. How do you ensure? What do you reason about? What's working well or what's not working well? So in that sense, all the more reason I thought it's a very dry topic. But needless to say, please stop me anytime, and we can answer any questions along the way. I'm also happy to answer any questions on any topic that's not related to this. So it could be vector databases, can be AI, can be agentic stuff, you name it, or storage layers or whatever you want to talk about. Okay, so we can, but obviously not during the talk. Right? So
let's get started, okay? So in some sense, this is sort of the clash of two communities or the convergence of two communities, what I call the database community and the distributed systems community. And we're going to talk about that. So databases been around for 50 years, 1970s. Relational databases, everybody knows them. Everybody has used something or the other once upon a time, maybe not the younger ones. They're like, what's a relational database? Why do people need it? And then, they introduced this notion of ACID, which I will talk about, what it means. And they introduced this notion of serializability. So usually, and they introduced this notion of a transaction where you have multiple records being written and read into in a transaction. But not that it's only one copy of each of the records. That was the prevailing sort of way relational databases evolved at that time. Now, completely independently, there is this whole class or community called distributed systems, which actually arose from even cache coherence and things of that sort. Didn't even necessarily they were not data people at all, and they were worried about saying, okay, they didn't call these transactions, they wouldn't call these records. So if you go back, they'll call it operations, they'll call it objects, whatever, right? When speaking in database language, they had transactions that operated only on one record. Okay, but this record had replicated copies, multiple copies. So the distributed systems folks essentially had multiple nodes having the same data, and they want to keep the data consistent, so to speak, across multiple nodes. So that was the problem they were trying to solve. Long back, the NoSQL kind of inherited that, if you will, that banner from them, and cast it into the language of databases and said, okay, there is a transaction, there is a record, here's multiple copies of record. And my friend Raj here did implement some of this, and that was quite a while back. So that's how the NoSQL world kind of evolved. But really, what's happening in the sort of the modern dimension is that whether you call it NoSQL, Cockroach, Gigabyte, those kind of guys are NoSQL. Like that's not at a spike. We're trying to do what's called distributed transactions. And distributed transactions means doing things to many people, but for our purposes, let's just say it's dealing with multiple records, each with multiple copies. So that's the setting, okay? So we'll figure out what this is, and what this is, and how we get to this point. And what is correctness here, what is correctness here, and what is correctness here. And it's somewhat non-intuitive. These two things are intuitive, and then something surprises you when you get here. So that's the story. Okay. Any questions? I mean, is the framing clear? Okay. Yeah, like I said, please do stop me if something is not clear. Yeah, a little bit more of a history lesson here. Back in the 1970s, so relational databases, all these, airline reservation system, banking system, they all worried about what's called strong asset properties. They didn't scale too well, but they were very, correctness was an important thing. And then around the 2000s, what happened was the internet era, the Google file system gave birth to this whole new class of systems where I said, okay, screw correctness, we'll get there eventually, eventual consistency, but performance is what matters. We sacrifice consistency for performance. And that's what it was in 2000s. We come today, 2025, these are converged. There are systems that want both performance and consistency or correctness. I'm being very vague here, we'll define this word shortly. Okay. So just on a time scale, that's how it looks. Okay, so let me sort of very quickly introduce asset transactions. Sorry, this looks like an undergraduate class, throwing you back. But it's important to make sure these concepts are clear. So a transaction or asset transaction, again, as defined 50 years ago, is supposed to be asset or have the asset properties, which means atomicity, consistency, isolated, and durability. Atomicity basically says that the transaction completes in its entirety or nothing happens. So you try to withdraw a balance, you try to make a transfer, you don't want something half done, right? So you want it completely done, or you want a failure which reflects that, so nothing happened. Consistency says take the database from one consistent state to another consistent state, so transactions should not violate any integrity constraints if blah, blah, blah. Isolated, we'll talk more about it, so I will not talk much about it. Durability is making sure, yeah. We're going to talk about consistency only to sort of, because it's a very overloaded term. First of all, consistency is used in the context of distributed systems gap theorem, and we're not talking about that consistency. Many people know consistency in that context. Leave it aside for now. In the context of ACID, what does consistency really mean? So people there's a meme that says, even the wiki page actually, for ACID will say NoSQL cannot be consistent. Okay, no NoSQL systems cannot be consistent or something like that. And that's not true. And the reason they say is it cannot guarantee something called referential integrity, which is a relational database concept. And the reality is Jim Gray, who's the sort of Turing Award winner, original father of databases, who sort of invented the whole notion of transactions. Even he says it's just a transformation that, takes it's a current transformation. That's all from one database state to another database state. And I'm dating myself. No, I was born. But IBM IMS 360. It's a very old hierarchical system. What used to be called hierarchical databases and all that. Is an ACID sort of compliant system versus object-oriented databases back there. And NoSQL today is also sort of ACID. So these all can be ACID systems. You don't have to be a relational database to be ACID. Long story short.
What is correct loss
Good. So set of constraints that you can specify. So for example, in most people publish, there can only be one better person to the value of priority. That's a priority. So it's a set of constraints that are unsatisfied. So you might say, that's all. What are those set of constraints?
So the transformation essentially leads from holds all the constraints in the data.
Correct. Constraints hold and transaction start.
Holds the lines.
Holds the index. The database state has changed from state to state.
Or if it doesn't.
Huh?
It also has no if it doesn't end.
Yeah.
As in if it crashes into that.
Yeah. Yeah. Okay, let's get into isolation, and this is the most important topic for today. Well, it all starts with the fact that transactions need to execute concurrently because you're not using your resources at once. So you can't just say, hey, I will execute one transaction after the other, because that's an easy thing to think about. If you execute transactions serially, it institutively right. I mean, how much better can you do in terms of in terms of concurrency of transactions? Not being isolated from each other. So the goal of isolation is you want to provide a safe guarantee that as those things are executed sequentially or serially, while they're executing concurrently. So that is the goal of isolation, right? So let's sort of look at a very simple schedule. Schedule is just a layout of the operations in some temporal order. And so let's say you're transferring $1,000 from A to B. This is subtracting 1,000 from A, adding 1,000 to B, and then read A, write A, read B, write B, other actions that go from the database. Reads and writes are the only thing that the database sees. These are actually not at the application level, so at least if you use a simple read write interaction with the database. And this one is basically sort of printing the sum of A plus B, okay, in some of the accounts. Now, needless to say, if your things did execute the way it did, this is you would get A plus B, which is 1,000 less than the real A plus B. Because if this had executed right off front, you would have got whatever that sum is minus 1,000, because You saw this 1,000. Okay. So this is not quite right. Okay. Now, a little bit more intuition correctness. Why is it not right? Well, let's actually represent T1 and T2. Let's look at a graph that represents T1 and T2. And at the edge from T1 to T2, if two actions conflict. Okay, what is conflict? Well, two actions conflict if they're operating on the same data item, and at least one of them is right. Okay. And if there is a conflict, there is a precedence edge. Now, why is this edge from T1 to T2 there? So this basically says that T1 has to come before T2. Okay. And why does T1 have to come before T2? Because T1 wrote A and T2 read A. So this is a write A to read A is a conflict. Okay. Similarly, read B to write B is a conflict. Because I read it before the write, I have to come before this. Well, that's what leads to the cycle. So this is a precedence graph. If there's a cycle, that's not right. So net, this is not a correct execution. Okay. So a little bit more. So let's look at another interleaved execution, which is correct. So in this case, things are interleaved. Okay. Except I had the read B before here. I moved the read B down here. And this turns out to be right, because I'm reading the B after the write of the B. I'm reading the A after the write of A. So this is almost like saying I did T1 first and T2 next. So that's what this is. So this edge disappears. Okay. But what does it mean? How do you formally argue this, right? So how do you formally argue this is something called serializability or serializable schedule. So that schedule that I showed, which I've repeated here, is serializable. What does it mean? Why is it serializable? Because it can be made into a serial schedule by swapping adjacent non-conflicting actions. So if two actions don't conflict, remember again, two actions conflict if they act on the same data item and at least one of them is a write. Okay. So you can take read A and push it all the way down because B is a very different data item. So there's nothing wrong just swapping. And once you end up swapping, you'll get T1 followed by T2. So that is how you reason about correctness, okay? All this is good, but reality, how do I implement something like this? Meaning, post facto, you can show me all of this and I can tell you whether it's correct or not, but I'm a running system, I'm trying to implement a database. So how do I ensure that I'll only allow such correct schedules, okay? Again, I'm not going to go into deep details, but the point is there are three standard mechanisms for, there's something called MVCC, but I'm not going to get into that. But the intuition is they don't allow, they have to deal with an action when presented with it, and they will sort of deal with an action in one of two ways. They will either not allow it if they think it's going to conflict. So there's a very pessimistic approach. Oh, something is conflicting. I'm not going to allow it. I'm going to wait. They will wait and do something. The other guy says, no, let everything happen, free for all. But all the rights will be on some private copies. Okay, so I want to expose the copy. At the end of the transaction, I will check whether I can commit or not. Okay, and whatever has happened before, am I conflicting with anything that happened before? If I did, I will back out. Otherwise, I'll go ahead. And timestamp order is another way some of you do this, where you predefine the order of transactions at startup time. Okay? At startup time, everybody gets a timestamp. And then we will not allow an earlier transaction to conflict with a later transaction. Again, I'm not going into the details, but the only reason I'm mentioning this is there are standard mechanisms that your databases use. Okay, let's keep going. Yeah, this is just a pictorial representation. What you want to take away from here is the execution of a concurrent set of transactions is equivalent to some serial order. That's what serializability tells you. That's the takeaway. There are lower levels, again, we're not going to talk about all of that. I will plant this thought for now. We will use it later, which is, and this is the whole point of the talk, that serializable schedules allow transactions to perform time travel. Okay, what do I mean by this? So I'm going to take two very silly examples. No database, if any database system did this, they would not be selling any copies of their databases, but still it's useful to talk about it. which is, let's say there is a read-only transactions. You can always accept any read-only transaction in a database and return empty result for all items. Why? Because when the database started, it was empty. So I just take my read-only transaction and pretend that it started, even though it came 365 days later, I pretend that it executed on day 0. It's fine. Serializability allows it by definition. Okay, it's important. Like I said, nobody will do this, but the reason I'm putting these silly examples is there's a real good examples coming up in distributed settings. Or immortal right. Okay, an immortal right is one where a single record transaction that's writing only one record, it performs a blind write, and on an existing record. Well, if you're performing a blind write on an existing record, I can pretend to do that. I can do nothing. Why? Because I pretend that I executed before that previous write. And serializability allows it. All serializability said is the concurrent execution should be equivalent to some serial execution. That's what it said. So it's okay for the transaction to do some time travel. But yeah, file this away, these silly examples, it becomes more important later. So I'm going to shift gears a little bit, and talk about distributed systems and replication in distributed systems. This is sort of remember the parallel, the other side of the brick wall. So we kind of talked about this side of things. We're going to talk about this side of things a little bit before we do the grand unification. Okay. Okay. So what's the goal of replicated databases? Okay, they should behave like single copy databases. So you should not be able to tell from outside that there is replication going on under the hood, right? That's the goal. And why do we do replication? Well, because in distributed systems, distributed databases with hundreds of nodes, some node or the other will fail at any given time. If you had only one copy, then the node that had that copy is not, that's not going to be available. That record is not going to be available. That is not acceptable. The whole point of this NoSQL systems was to sacrifice consistency, which we'll come to later, to get availability. Okay, so that's why. So you need replication, but it should give the illusion that there is only one copy of the data item. That is the goal. So what, there's something called linearizability, and again, I will not define it too formally, but I'll just sort of gloss over it. The concurrent operations on a data item should be linearizable. All that is saying is there should be a linear order in which operations on the data item happen, right? So it can't be like, it cannot have the effects of O2. O3 succeeds, but then O3's effects are not seen. So there is the simplest way to think is there is a single lineage for the data item. It goes from version 1 to version 2 to version 3 to version 4, and that's what all copies will go through. Okay. Yeah. And the gold standard for C, unfortunately, consistency again, is in CAP is linearizability. Again, I don't know how much. I mean, I'm not going to tell you what CAP theorem is, but if you don't know, it doesn't matter. For our purposes, all this means is, in this case, there are sort of operations on a single object, on a single record, and all this is saying is some concurrent execution of these operations is equal to some linear execution, either this linear or this linear, doesn't matter, or some order actually. This linear doesn't matter. Okay. But there is a slight subtle difference. Can somebody tell me what is the difference between execution? What did I say before, and what have I said extra now? I said real time. Some real time serial order. So I didn't say why I said it. By the way, the real time here is again another overloaded word like consistency. Real time doesn't mean highly performant or something that finishes fast. This just means small clock time. It's just real. Okay. So what is this some real time serial order? Well, for linearizability, it turns out if you look at this ON, notice that I have ON here and here. In both cases, it's coming in the end. ON could not have come anywhere else because ON starts after both of these finish. This starts after both of these.
To maintain the monotony of time.
Yeah. So you can, the concurrently executing ones, you can order them anyway. But if they're not overlapping in time, then you can't do the travel back in time magic that we did with serializability. So that's the whole point here. So the cheating we did where we said read-only transactions will return zero value, nothing. So that cheating is not allowed here. So that's a very key difference, okay, in terms of from a linearizability. Any questions so far? Yeah.
Why wouldn't relational databases be worried about this?
Why wouldn't they not? Great question. Thank you for asking. Because they did not have to, okay? So it turns out that if you have only one copy of the data item, and if you got serializability, you also, in some ways, got real-time order. So that's why I said that was a mythical construct. No, I mean, it's harder for a database system to travel back in time arbitrarily. It's not easy because I only have one copy of the data item, and things are going forward. I've updated it. The guy who has updated is gone back, long and gone away. Now, how do I get the earlier version? It's not easy unless I'm maintaining earlier versions and deliberately take you there, which is a separate set of topics. We won't open up that kind of works. So the point was it is not required for them to worry about this. So that's solid theory, solid foundation for single copies. Okay. These guys obviously realized that when you have multiple replicas, you needed to be careful about this real-time ordering. And so that's why they, the distributed systems guys did it. And what you're pointing out is the crux of the problem if you're not careful with distributed transactions when we put these two things together. Okay. Any questions? Okay, yeah, keep firing away. I mean, and don't worry about whether it looks stupid or not. I don't think that there's no stupid questions. There are only stupid answers, which will come from me. So please. Okay. So linearizability is also called strong consistency, and traditionally things called Paxos and Raft, are two popular protocols that have been used. Yeah, I mean, I promise then I will not keep using Aerospike much, but here, I mean, I don't want to mention this here because I do think it's very unique. It's very novel. And we're just writing a paper on this, which is that we have a protocol that, does better than Paxos and Raft in some sense, that we kind of optimize availability way more than Paxos and Raft, under the assumption that failures are of two types. Either there are a small number of independent failures, which is everybody is equal, or entire availability zone fail. It's not like randomly 10 nodes here will fail. A few nodes here will fail, 3 nodes will fail, but it's not like if you have 100 node cluster, 30 nodes will fail across 2 availability zones. I mean, that requires a higher probability, very low probability event. Entire availability zones can fail, or a few nodes here, a few nodes there can fail. So anyway, I won't go into the details, but it's a very elegant kind of a way to think about it. Okay, which brings us to distributed transactions. Before I go there, I mean, at this point, we are trying to sort of merge what we learned in serializability and what we learned in linearizability. And just to recap, right, serializability says concurrent execution is equivalent to subserial execution, equivalent, although we are still executing concurrently. The one gap that we had there was we allowed time travel, which, like I said, like he asked, is impossible in a single copy database. That's why I had to come up with contrived examples for single copy databases, but I'll come up with real examples of distributed transactions that can happen, distributed databases that can happen. So that's where this is leading up to. And then, of course, replication or strong consistency. That's how you get linearizability. That's simple. You've probably heard Paxos. You've probably heard of Raft. That's one of the ways you kind of get that done. name your database, whether it's Spanner, Couchbase, Cassandra, everybody will use some variation of Paxos or Raft. Okay, pretty much. The entire industry uses one variation of Paxos or Raft, except Aerospike, of course. Okay, so before I go, so now I'm going to sort of talk about things in a distributed setting. So the setting now is a transaction is operating in multiple records, and each record has multiple copies. Okay, so that is the setting. So multiple records, multiple copies for each record, that's a transaction. That's what a transaction impacts. So let's look at a particular transaction. This is not a very particularly, this happens to only work on one record, which is record X. So T1 updates record X, and so maybe, initially it was 5, it updates it to 10. And this is sort of being replicated. And let's say it's replicated asynchronously, which means we're not doing strong consistency. We're not guaranteeing linearizability. Okay. So what that means is this will happen, and after a while, this can happen. Okay. And so what that means is when I read the record X, I can read the earlier version of X, although in terms of time, transaction 2 happened later. This is perfectly legal if the system is not guaranteeing linearizability. And this is also perfectly serializable. Why? Because this is as though T2 executed before T1. There is no problem from a serializability point of view, right? So this is what is called a stale read. So serializability can give you a stale read. Now we are traveling back in time because we have multiple replicas with serializability. With one copy, we could not, modulo my contrived examples. But this is a genuine case that can happen, okay? Yeah. Yeah. Because it's reading from a different site or different replica. These replicas are not synchronized. That's all I'm saying. If you do not synchronize these replicas, then serializability can give you stale reads. Serializability alone can give you stale reads. So where I'm going with this, I mean, just to sort of view the punchline, I'll say serializability alone is not enough. Linearizability alone is not enough. And as I'm shortly going to show, putting both of them together also is not enough. And that's all part of our talk, okay? Which we'll get into. So this is an example, probably the most complex example, where I'm going to tell you that having serializability and linearizability, the gold standard for relational databases, the gold standard for distributed systems, is not enough. You can't just put them together and hope distributed transactions will come out. And that's a part of the talk. Okay. Okay, so sorry, I'm going to use sort of American examples here. So, I mean, but nothing very hard to follow. So there are two accounts, okay, for somebody, some called checking and savings, which Anirudh tells me I should be calling them savings and current. I didn't change them, but yeah, checking and savings. And let's say the original balance was 30K in one, the 10K in the other. And what's going to happen is somebody applied for a loan, and that in the background, the loan starts checking whether your total account balance exceeds 300K, because that is the condition for granting you a loan. Okay, so that they applied for a loan. This is happening in the background. Now you are actually very careful, so you know this is going to happen. You actually desire to transfer 300K because you're traveling somewhere else. So you say, look, I'm going to transfer 300K out of my checking account because it's easy for me to give a check, in a foreign country, and I'm, going to give it to somebody else. But to make sure I can give that 300K, I'm also trying to make sure that I deposit 300K before that, because there was an IRS return, which is a tax return that came. So you call your spouse and say, hey, can you deposit the 330K IRS tax refund into the savings account? So they put 330K into X. Okay? And then they call up and say, hey, you're all good. You can do your 300K transfer. I mean, so at this point, do you expect the loan application to fail? in a reasonable setting? It should not, right? I mean, we're trying to make sure that the balances are kept above 300K very carefully by doing this complex dance. Okay. So I'm just going to show you a mechanism by which a sequence of events. Now, I'm not saying what will give you the sequence of events, but the sequence of events is serializable. It's linearizable. So let's see what the sequence of events is. So you first begin transaction 1, which is that whole load transaction, and then you read X here, you read Y here. Meanwhile, transaction 2, which is your spouse depositing, you begin here, you write commit. Note that this read happened before the write. Okay, we'll just record that for now. And yeah, like I said, don't worry about how this is implemented. Obviously, if you use strict two-phase locking or something, this may not happen. It could happen with timestamp implementations, and let's not worry about that for now. Okay. And similarly, this is transaction 3 where you begin write Y commit. So write Y is this 300K transfer, right? So Y. So we could even show the values actually. Yeah. So this X is 30K, this Y is 10K, because remember, there's 310K, there's 300K went up. So okay, let me pause here. So essentially, this loan application fails. Okay. Notice that this is still serializable. Can somebody tell me what is the equivalent serial order? I mean, what is this execution equivalent to in terms of transaction order? What executes first? What executes next? What executes next in the equivalent serial order? Huh? T3 followed by, what is this? T1 followed by T2, I believe, right? T3 followed by T1 followed by T2. This is the equivalent serial order. So as though this went first, okay? Then this went, then this went. That is the equivalent serial order. Anyway, I mean, it's a pretty complicated example, but these are the kind of things that you have to be careful about when building distributed transactions. But however, although T3 happens before T2 in the equivalent serialization order or in the equivalent serial order, T3 happened entirely after T2 in real time. So serialization is not enough, okay, in the context of also these, I mean, things are linearizable here and so on and so forth. I won't get you into details. I will just give you the punchline. So just linearizability alone, of course, is not enough. It doesn't guarantee serializability. You can have something like this, where it's not serializable. Serializability does not guarantee linearizability. We saw that stale reads. There are things that are serializable but not linearizable. Having both is not enough either. So it's you get into what's called causal reverse. Anyway, why does all this matter? Yeah, it becomes a headache of the application programmer to deal with things. Unexpected behavior, frustrated users, and you have to, of course, carefully design your application logic to avoid inconsistencies. So I'm not going to. So anyway, I'll leave you with this thought that there is something called strict serializability, which is what you need in a distributed transaction setting, which is essentially, look, it kind of merges the ideas from linearizability and serializability from a correctness perspective and puts some real-time serial order. Okay, so all that is saying is, wait a minute, if transaction N happens or starts after you guys finish, I don't want an equivalent serial order in which TN travels back in time. You better respect that real-time order. Okay, so that's called strict serializability. Oops. Last. So what does all this mean? What's the takeaway, right? So if you're a database system builder, then you have to be careful. Distributed transactions are nuanced. And I think this was actually Cockroach DB and Yugabyte walked into this problem. And that's why this is a very famous problem. They still have, obviously, it's too hard for them to now fix because it's so entrenched into their thing. And again, we can get into exactly why it happens. It's some combination of time, using timestamp ordering as your basic concurrency control, but keeping timestamps synchronized across sites is very difficult. So we can talk about why exactly it happens. This won't happen if you just use strict two-phase locking, for example. Anyway, so that's as a database system builder. But many of you will just be developers. You're all big data guys, but you're not building databases. You're just using databases. You want the right thing to happen. Then make sure you understand what guarantees you get out of your database, right? And otherwise you'll be fielding a Sunday morning call from an irate customer saying, you know what, I tried to do this carefully orchestrated. I deposited the check, then I did the transfer, and here you are. You rejected my loan application. Cool. I'll stop here. I hope I left enough time for questions. Yeah, that's good. I think I want to finish in 40 minutes, 45 minutes, because I want to leave more time. And like I said, I'm not restricted only to this topic. We can talk about any topics as part of the question Q&A. Thank you.
I have seen different use cases for Aerospike. So some people are suggesting as a replacement for Redis, some people as distributed SQL.
Sorry, I didn't hear your question.
Basically, different people are using for different purposes. Some people like suggesting there was one application, leaderboard application using Redis.
Yeah.
And somebody commented on that saying that why don't you use Aerospike?
It's a good idea. Yeah.
So what is the targeted use cases? Like I have seen like different use cases for Aerospike.
So here's what I would say, right? I mean, and Raj here knows about this. So when we started, it's an evolution. When we started, we were largely used for caching use cases. That is true. I mean, caching was an important use case. Slowly, what happened is we became an operational database, what I call an operational database. What that means is anything in the real-time serving stack of a modern enterprise. So you're a modern enterprise, you have machine learning algorithms, and you are doing inferences, okay? So if you're making inferences, you need a lot of data. As you're making inferences, either as a feature store, user profiles, whatever it be, right? And then Aerospike is the sort of the database that holds all these things. At that point, it may not be a cache. In the sense, it may become the source of truth. So the difference between cache and an operation database is, are you the source of truth or not? Okay. So it actually can become the source of truth, especially, if you have things like, again, it depends on the application. If the source of truth can tolerate, what I would say, older values, then you can use more relaxed consistency across clusters, which is using eventual consistency. Otherwise, you have to use something called strong consistency, linearizability that we talked about across clusters. And of course, the next step is not just an operation database that uses strong consistency, operation database that supports, that needs distributed transactions. So you can have operation databases that have, maybe you're updating a bunch of products at the same time, bunch of catalogs at the same time, whatever it is, right? So, and you want that to be atomic and be independent of each other. So it started caching, used as a feature store in many contexts, used for, I would say invariably what I've seen is it's used as the data store that sits with an ML inference engine. That seems to be the most popular use case that I've seen.
Like fraud detection.
Fraud detection, anomaly detection, recommendations, name it, search.
Those use cases, we don't need to distribute.
Sorry?
Those use cases, we don't need distributed transactions, right? Or do we need?
No, I mean, if you are it depends, like I said. many situations you don't need distributed transactions. The first, you may even get away with eventual consistency. Then there are a class of problems for which you need strong consistency. Okay. For example, let's say you are keeping, so eventual consistency you can get away if these are machine learning models features, okay? Because it's okay. It's not, I mean, you started yesterday's model, it's not the end of the world. But then they're also using payments, okay? They're using record payments. So Raj transferred X money to Y, okay? But that whole thing is in a single record. We're not doing MRT, okay? We're just recording who sent what to whom, and then post-factorly. But that record better be consistent across all the copies. So at that point, you need strong consistency. But not pretend that we don't want to keep one record that Raj did. We want two records, Raj and Sesh, and deduct exactly what we went through, deduct X from Raj and add X to Sesh. Then you need MRT. So the scope of use cases increases as you add more features. Yeah.
You took us through the history of, how
Sorry.
you took us through the history of databases where people back then, they thought of, distributed transactions being something they don't have to worry about. And, they thought of it as, they would never come across a situation, right? But now that we've reached a place where the compute has gotten very strong, unlike before where now we can have real-time, like soft real-time transactions. Where do you see this heading? Do you think people will just move towards changing their definition of correctness of the transactions based on their use case application, and then finding performance there? Or do you think more can happen on the architecture side of things? Or where do you see this heading towards? Or how do you think this could get better or faster?
So I want to make sure I repeat the question and I understood the question. So I think your question is, does everybody need distributed transactions the way I've defined it and the correctness criteria that I've defined, the way I've defined it? Is that the question? Bottom line?
In essence, yeah. If we can't make it faster,
Yeah.
is that the way we go?
Fair enough. I think, yeah, that's how databases distinguish themselves, right? So can you provide even more correctness and better performance? So whichever database can provide that will at least want to claim for that use case. But having said that, so here's how I see it, okay? And I just went through the situation. There are use cases where eventual consistency is good enough. There are use cases where consistency is good enough. There are use cases where you need distributed transactions. Now, so that's in terms of correctness. Now, you take any database, it is sort of trivial to say that the DB1 will do eventual consistency faster than strong consistency, faster than distributed transactions. And DB2 will also do it. Now, what the relative speeds are is what, for a given application, somebody will say, I want eventual consistency, I want strong consistency, I want distributed transactions. Who can provide me that at the, who can provide me that at the fastest speed? And do I need that? I mean, sometimes you may not care about the speed. SLA may or may not be important. There may be other things that are important. I mean, we have sort of focused this whole talk on correctness, right? But there are so many other features that people care about in the database. So it will come down to what they want, whether the SLAs are satisfied or the correctness that they want. So you have to reason about all of it. You have to reason about what correctness you want, what SLAs you want, what else you want, and what's the right fit.
Hi, good evening.
Yeah.
There was a slide around distributed consensus. I noticed you spoke about Paxos and Raft. It could be a bit off topic, but I want to understand what is Aerospike doing in terms of consensus? How is it different from Paxos, Raft?
Yeah. So I'm going to, I think, okay, so let me tease out a nuance there, which is distributed consensus, in my opinion, is a more general problem than replication in a database. In the sense, you can use distributed consensus to sort of get replication, but you can use distributed consensus for other things too. You can do leader election, you can do, whatever, right? So just wanted to point it out. So I'm going to focus on perhaps on replication. Okay, so The way, I mean, therefore, obviously, like I said, taxes and draft can be used for, for replication. The way Aerospike is different is, okay, so the simplest way I can express this is, here's the crux of taxes and draft. What they say is it's called majority, quorum, consensus, whatever, right? So essentially, you will have, if a majority of nodes are available for a partition or a shard, then that shard is available. Okay. So I'll make that as simple as that. So now you might, so I'm trying to, okay. So let's say there are three, let's just say there are your entire quorum is three. Okay. So what Paxos says is if I have two of the three available, then I'm good. But if I lose two nodes out of those three, then I'm not good. I'm not available. But realize that losing two out of a three is not, it's a small number. Okay. Out of it, of course, the cluster itself could be large. There could be a 100-node cluster, but for a single shard, you will only have 3 copies. There are many, many shards in the database system. So what you're saying is, if I lose any two, okay, of the 3, then I'm not available. So the way we change it is we say, as long as you have a majority of the entire cluster, that means out of 100 nodes, if you have 51 nodes available, in most cases, we can make every shard available. And I don't want to get, I mean, obviously, I have to explain to you the entire algorithm. But the point I'm trying to make is, therefore, our availability goes up. So small number of independent failures don't hurt us, but that's what hurts Paxos or Raft. Okay.
That process might affect the leader election as
So yeah, now we're getting into a lot of technical details. You seem to know a lot of the subject. I'm happy to definitely discuss this, but that's yeah. I mean, we can talk about it.
Hi.
Nice to see you.
Yeah, good. So I was just looking at not really the application side of it, but actually what goes in actually implementing these algorithms, etc. So they're kind of fairly complicated things to do. And how do you kind of verify the correctness of these algorithms? Like, do you use systems like TLA plus or something to kind of verify the algorithms, etc.?
Absolutely, great question. I mean, TLA plus is something you should start with, but honestly, I mean, that is at a conceptual level, you want to be, it will prove something, but the implementation, needless to say, is far more detailed, and TLA plus doesn't capture all the nuances of race conditions in a distributed system, that message getting reordered. So there's a guy called Kyle Kingsbury, okay, and he runs something called Jepsen test, a very famous test called Jepsen test. So he's like Kingsbury is the king of testing, okay? So he has mastered the art of testing databases, whether they satisfy strong consistency, databases, whether they will give you strict serializability, blah, blah, blah. So I'm just saying there's one independent auditor. So for example, to your point, if I were to go to a customer and tell them, hey, I do this, they'll say, okay, you might even have a proof for paper, you might have a TLA plus, but if Kyle endorses it, it means something. And what are we doing? He just has a battery of tests. And so do we. I mean, we all internally. So long story short, it's just testing, but there will always be some coverage that may not be there. Except that guy has been doing this for every database for so long that his test coverage is enormous at this point.
So you're saying the test coverage is good enough to kind of believe these things are working? You don't really need more stronger frameworks to kind of prove that correctness of these things for databases. I mean,
I would love to discuss this more. I'm finding it hard to believe that formal systems are going to be powerful enough to capture the nuances of a complex implementation of thousands of lines of logic. With distributed system message passing. I'm not convinced that formal methods will work.
Not that I have any experience with it, just kind of curious to see, like, when you work at that scale, like, how are you kind of practically solving those issues? That's all.
This is the industry norm today. If Kyle says it's good, then there's more belief. Okay, I mean, but it's a great question. Yes, and yeah.
Something to add on to that point, right? You mentioned that
So there was this article I read recently where one of the chief scientists, I think, in Azure storage, what they actually did is they got an LLM to go through their whole code base and generate a somewhat okay TLA plus spec. And they found a couple of very interesting bugs through that. So, maybe that's where the intersection lies. Where instead of, because it's hard, right? Like reading TLA plus is hard, writing correct TLA plus is probably like infinitely harder. So what they did is they got I think a bunch of a whole ensemble of models to go through their code base, generate somewhat correct TLA plus, and they ran that to sort of verify the system. So maybe that's where the intersection is, right? Where you can obviously, I think Jepsen testing is very, very good on its own. Like like you have to read the reports to get it right. He is thorough, and it's like a nightmare sort of situation if there's a Jepsen report on your database and you didn't know that it was happening. Right? So those are like make or break kind of things, right? You take a serious reputation hit, and the whole of TechTwitter is going to be mad at you for a couple of days, and that stuff. So that's the level it's at. So it's a very, very well established thing. But yeah, I don't know. Who knows? Maybe there are interesting future elections.
Yeah, I mean, LLMs can take you somewhere, but I would still say the state of the art today is Kyle, but I'm not ruling out something that happens in the future. Yeah.
Hi, so my question is not related to distributed transactions, but since I've been around in the database world for so long, I wanted to ask your thoughts about like graph databases because I've started taking an interest in graph databases a couple of months ago. So from what I read a lot, there's a strong case being made for telling that okay, you can just represent like the nodes as like tables and like you can just model the same thing in a SQL format, and you don't actually need a graph database. But what I think is that it's not just about the storage, but it's also about like the algorithms that you run, which are very specific to graphs. Like PageRank, for example, the way you run it in a graph DB and in a SQL DB is very different. So I just wanted your thoughts on that.
I think you hit the nail on the head. I mean, it's not about storage, it's about what algorithms or what queries you run, right? So, I mean, you can store anything, you can store anything at the, but in particular, I mean, so I don't know, I'll bore you with some theory, okay? So there is, obviously SQL is based on what's called relational algebra, which is the origin of how, that's what Ted Cord invented, and it's well known that relational algebra cannot compute few things like transitive closure. So what is a transitive closure? If you take a graph, then you keep going and you have to say what pairs are reachable from each other. So that is the transitive closure of a graph. So what all pairs are. So for that and I'll part that. The fundamental reason, so what you say is no SQL statement can represent or can capture this property called transitive closure. You might have also heard of the word SQL is not Turing complete. You've probably heard this. Relational algebra is not Turing complete. What does it mean? It can't do everything that a Turing machine, which means a PC, computer, server, it doesn't matter. But that can't do a C program sitting on it. You can't do, SQL cannot do everything that a C program can do. But that's not true for a C and a Python. Yes, you might say, hey, it doesn't have that library, this library. But yeah, given an infinite time, you can recreate anything. So when in C and Python, there is no expressive power difference. SQL is by definition not in the same rich expressive power. Anyway, so why did I say this? So what SQL lacks is, so to chase one edge, it needs one join. Okay, so the fundamental problem is to go one edge, it needs one join. To go on the edge, it needs one join. And with the transitive closure, there is no end. I mean, you don't know how many times you're going to keep looping around. So, I mean, how many, you can't stop this number of joins. But coming back, let's not even worry about transitive closure. Let's say the graph algorithm that you're using just requires, 3 hops, 4 hops. So you basically say, okay, start from all nodes that have property X. Maybe there are 20 of them. From those 20, step out 1, step out 2, step out 3, and then collect some property. So to do this, you need to do this joins multiple times. Okay, you need to do at least 2, 3 times. So that's where SQL starts sort of tailing off.
That brings me to a second question. So
Yeah.
graph data is still everywhere, but I don't see graph databases being popular. So why is that?
It's a great question. It's a great question. I think it just comes down to whether so it comes down to whether you need graphs of that magnitude and whether there are enough use cases for graphs of that magnitude in terms of. So if a graph fits in memory, and you can just load it, there are probably enough graph packages that could just work. So maybe you don't need the persistence, you don't need the whatever, you don't need the database properties, which was what was a graph database provides in many use cases. So they can get away with graphs in memory and blah blah blah. Right. So
Thank
yeah.
you.
Any more questions?
One comment on the SQL form, right? So, SQL is not in that form, right?
Yeah. So I take back. Yes, they put in the trusted closure operator. You're absolutely right. I mean, I was being a bit, what shall we say, loose there. I think what is rightly pointing out is SQL back in 1992, 95 was a very much more faithful sort of a relational algebra thing. They kept adding more and more power, and they introduced this notion of recursive queries or whatever. Yeah, so that's fair. So I should not say SQL, I should say relational algebra. But nevertheless, my point about, thanks for pointing that out, Raj, but my point about whether it's, even if they have that power, they still, to go from one node to another node, they need a join. That's the idea. Anybody online? We can't ask questions, okay. Okay, cool. Did we stop?
Any other questions? Anything? No such thing as a question. Please.
Yeah.
Okay, what is the correct? Also a function of observer. Database being correct is one, what observer sees such correct is a different. Your thoughts on that?
Yeah. No. In this context, what I meant by correct is a definition that is, it's intuitively understandable. So for example, I said serializability is correct and linearizability is correct. So it doesn't mean that others are not correct. For example, I mean, just to be clear, it's the highest form of correctness. There are lower forms of correctness. I mean, maybe that's what you're getting to, okay? So for serializability, there is something called read committed, there is snapshot isolation. So there are many degrees of correctness. And usually, so what serializability and linearizability give you is, in some sense, you can't be more correct than that. There is nothing, it's impossible to construct a system. Again, I've not thought through this, but I'm claiming this without proof. But if you lower the level of correctness, you will not, you could have this class of problems, but you definitely solve another class of problems. So there is the way they define is there is a class of problems that you can have if you are completely unconstrained. And then every level of correctness kind of seals more and more classes of problems until you get to serializability, at which point, yeah. So that's really what correctness is. So you're right. I mean, you can say read committed is correct. I mean, if that's your expectation that I will only read committed values, I don't care about anything else, then that's a perfectly fine isolation level.
Because most of the world just runs on read committed.
Yeah.
Though is there, nobody really uses it. In reality, also
that's not true. I mean, I think it was true. You're right, probably from your.
Maybe, but
yeah.
Most of the even in SQL.
Today I'm talking about. Really? Yeah. Today SQL databases may not use it. You're right. Well, I would phrase it slightly differently. The default setting they ship it with is read committed or snapshot isolation or whatever, and somebody has to take careful look at it and say, hey, this is what works for me or doesn't work for me. So my point is also, I'm not saying you need strict serializability, but make sure you're willing to live with these challenges. Yeah.
So as a function of what you're doing, you get to see market trends pop up a little early, and you have customers that you get to speak to on a fairly regular basis, right? And I'm sure you're also well in touch with folks who are actually doing research in databases. So could you maybe tell us a little bit about what you see as some very interesting emerging directions in the field of database systems research?
That's a good question. Obviously, databases is an old field. A lot of things have water has flown the bridge. I think definitely there's a new class of models. We call it multi-model. Graphs, vectors. So basically, richer data modeling capabilities, right? Data modeling capabilities and languages on top, whether it's Gremlin, Cipher there or approximate nearest neighbor, which is like essentially a search, but it's a database problem. Although keyword search and text search conventionally have not been a database problem, or it grew separate or independent of databases. So that's one set of things. I would say the other set of things is absolutely with storage, cloud storage, what's going on there, how do you sort of leverage modern trends in cloud storage, that's whole sort of things. The division of labor, if you will, between what all the storage can do and what the database needs to worry about is changing because the storage has replication underneath, it has strong consistency underneath. So potentially you can build a database without worrying about replication, right? So those are some trends, and so yeah, there are lots of interesting things. Definitely both on the application, the data modeling side as well as on the storage side that are happening. Yeah.
Okay, since I have the mic, I'll hold you hostage for one last question. Right. So a lot of the people that you see in the room are fairly young. I recognize some of my college juniors here, right? So in that sense, right, what advice do you have, drawing on your experience, for folks who are younger and still want to be very involved in the data systems field, not just from a application developer point of view, but from a systems builder point of view?
Look, I think it's the same advice for anybody in any field. You got to be curious. I think you got to be. There's just so much happening every day. You got to be curious every day, and you got to sort of say, ask the tough questions. Don't take anything for granted. I might have said a lot of this. Raj will never believe what anything I say. He will, and that's the right thing. It does. Because out of 10 times, I'm probably wrong 8 times, and he'll catch me 4. But the score is equal. He has not caught me the other 4 times. You got to be terribly curious. That's all I'm saying. Be passionate about whatever you do. I don't care whether it's databases, whether it's AI, whether it's ML, but really be genuinely passionate about your work, right? And you should, if you're not enjoying your work, something is not right. So you're not doing the right thing. It's probably the wrong job. Yeah. Yeah.
For people who don't know, this meetup has been cooking since April. Thanks a lot to patience from Anirudh and Sesh, and then a whole bunch of people who've been involved in doing this. And what else? I think there are lots of curious people around here. You should definitely talk to Raj. Not for the reasons that only Sesh mentioned, but also Raj has been volunteering to review a lot of the talks that are going to happen at the Fifth Elephant in 2.5 weeks. So if you want to know more about grilling, you should talk to Raj. There's also Pramod Biligiri over there. There is Anand. I think Sesh, you're definitely going to be late to dinner because you've attracted a lot of people who want to meet you here. So we'll stop here. Please do talk to each other. We have a request before we hit the pantry and networking starts. We want to do a quick group photo because if we don't show it on the photo, it never happens. So let's just tell people that systems is great because 60 people came here and beat Bangalore traffic.